So I think we have been talking about online reinforcement learning and exploration versus exploitation trade-off over the past week. So let's just wrap up this. So we have been talking about online reinforcement learning. Essentially, we look at a lot of regret, time complexity, and space complexity. So let's consider like run an algorithm for t iteration, run algorithm for t episodes. So we're asking like what kind of guarantees we can provide. So there are a lot of metrics we're looking at. First, we're looking at what kind of different algorithm, and then we look at the regret of algorithm, and we can look at the time complexity of the algorithm, and then also the space complexity of the algorithm. Okay. So historically, there are a lot of earlier algorithms where I would say the earliest algorithm that achieved like sublinear regret is so-called E-cube or Rmax. Those algorithms we haven't introduced in the class, but basically the regret they can achieve is something polynomial in terms of HSA and times t to the 1 minus alpha, where alpha is not very good. Okay. And later, there is some other algorithm called UCRL. This algorithm is different from the algorithm we introduced in the class, where the algorithm we introduced in the class is like a VI-UCB, where we put an up confidence bound on the value function. This put a confidence bound on the transition. On transition. And it would require at least square root of s squared at regret. Okay. Regret is at least this. So more importantly, this will actually pay something s squared dependence, which is the reason is like they put a confidence bound on the transition. We kind of like emphasize this this very important difference in the simulator setting, where our sum complexity is a scale with SA instead of s squared. Well, in a regret, like you're basically putting everything in the square root. But basically this UCL, because it's not doing very tight, so it still pay s squared dependency. So what we have introduced in this lecture is the first algorithm is UCBVI. And specifically the algorithm we introduced in the class is a Hoft inversion. Hoft inversion of bonus. The regret we receive is O tilde square root of h cube SAT. And the time complexity we will use is we can easily count that in every episode per episode, we're gonna basically doing an entire path of value iteration. So that will take some HS squared A time. So the total time would be Ts squared A. We will actually explain this later. But basically because due to in every episode, we're doing a full path of like value iteration. And the space complexity is something like HS squared A to store entire transition. And in the class, we also mentioned there's a Princeton version of bonus, which can achieve slightly sharper regret guarantee, which is O tilde h squared SA. And it would be the same time complexity and space complexity. So the benefit of using Princeton bonus, as we said in last lecture, is the sharper bonus you use, the better regret you will have. Okay? And the only complication is the Princeton requires some variance estimation, so the algorithm is a little bit more complicated. And in the last lecture, we also introduced the Q-learning UCB. And the regret guarantee for Q-learning with UCB is O tilde square root of h to the fourth SAT. Slightly worse than the UCB VI. But the major benefit of Q-learning is in every episode, we're just looking at one trajectory, and we're only doing update on that trajectory. So the time is O tilde t. Okay, everything is O tilde. Probably take some log factor. This is not true. And the space complexity, because we no longer need to store the transition, we only store the value, so it's a HSA. So we save an S factor. This is like model-free algorithm. And finally, we can also have the Princeton version. And that will give you a slightly better regret in terms of H dependency. Okay. So we have been giving a lot of upper bounds, and a natural question you would ask is whether those are optimal or whether we can develop some better algorithm, for example, like UCB with some other bonus, like much sharper bonus. Can we actually do a lot better than those guarantees? So it turns out we have been talking a lot about a lower bound, like multiple times. So this is, again, information theoretical lower bounds. You can actually prove the best you can do is actually just the square root of H square SAT. So no algorithm can beat this. Okay. So a few remarks. Essentially explain the table. First is UCB VI needs to do a full path of value iteration per episode. This requires like essentially the time complexity to do the value iteration is you have H steps, and per steps you're doing like a matrix vector multiplication. So it takes H S square A time, or like a flop compute. So this leads to this per episode. This leads to total amount of time is T square TSA. Okay, so that's why we put a TS square A here, and why this is like a lot worse than Q-learning, where essentially in every episodes you're only like only look at trajectories and doing computation based on trajectories. Second one, we kind of like already stated this in the last lecture, that a Princeton bonus require variance estimate, so it's more difficult to compute. But give sharper regret, and which will lead to a sharper sample complexity as well. And finally, we also notice in terms of regret, the UCB VI with a Princeton bonus is already the optimal. We call it near optimal regret. where this near optimal means like up to some log factor. Okay, we will see today like the lower bound, we typically like do some expectation and we don't have the log factor. But the upper bound, we do the hyperability, we have the log factor. So eventually, if we don't really care about the log factor and this UCB VI with Princeton bonus already match the lower bounds. Okay, any questions on like this summary of online reinforcement learning in the tabular setting so far? Okay, so if no questions, I guess we will move to the next chapter of this lecture. We're mostly talking about lower bounds. So far we have been mentioning this lower bounds for like multiple times in this class. We only very vaguely say this is like some information theoretical lower bound, like due to some statistical noise, but we never like give a precise definition or something. So we will dig more into like what type of lower bounds we want and how we're gonna achieve some algorithm independent lower bounds. Okay. So for the start, for simplicity, we will first focus on the multi-arm bandit case for this lecture. In the next lecture, we will talk about how to generalize it to Markov decision process and reinforcement learning. But a lot of key ideas are already contained in like establishing these lower bounds for multi-arm bandit. Okay. So recall what kind of lower bounds we want to achieve in multi-arm bandit. Whenever we talk about lower bounds, we usually want to say lower bounds will give some guarantees to say some algorithm is already optimal. So I think the first thing is we look at what kind of upper bounds we want to match, or we want to like provide guarantees that this upper bound is already tight. So just to recall, in the multi-arm bandit, we have guarantees. We have following regret guarantee for the UCB algorithm. Okay. So the theorem is the following, that with probability at least 1 minus p, the regret of a UCB algorithm is at most the following, that regret t summation from 1 to capital T Ri star, which is the optimal reward you can achieve. Achieved by pulling the optimal arm, subtract RIT, the reward you're going to achieve by pulling your arm. We say this is definition of the regret, and the UCB algorithm will guarantee the regret will scale with upper bounded by some constants times square root of AT iota, where iota is this like log factor. So in the previous lecture, we have introduced this regret guarantee. So the reason we introduce multi-arm bandit like UCB algorithm, one of the reasons is like this field has been studied for a very long time. It turns out this algorithm is like the optimal algorithm. This is like the best algorithm you can achieve. So today we will actually prove a lower bound, saying no algorithm can achieve better than this. So let's first think what kind of statement will basically say this fact, like no algorithm is better than UCB in terms of achieving this regret. Okay. So the theorem we're gonna prove today is something like following. First, we will say no algorithm better than UCB. So we do need to say for any algorithm, okay? We don't need to restrict to a certain class of algorithm, like doing this operation, doing that operation. We just want to have the strongest statement that is for any algorithm. Algorithm A, which can be even random algorithm. So we want to say even the random algorithm cannot beat our UCB. Okay. And this is the algorithm part, but on the other hand, like we have to say something about the problem, because for any algorithm, like if the problem is easy, and then we won't have like any lower bounds to say the regret. So we'll actually say there exists a multi-arm problem, non-bounded problem. So this problem can be very specific to algorithm A, like which is the hardest multi-arm-bounded problem like regarding to respect to algorithm A. So different algorithm may encounter difficulty in different multi-arm-bounded problem, but we just want to find a multi-arm problem that is the hardest for this particular algorithm A. So that we have the following, that the expectation in terms of algorithm A, because we might be random algorithm. So this is a taking expectation over the internal randomness of algorithm A. We say the expected regret of T round is at least some constant C times square root of AT. Okay, so we know there is no log factor, but we will do expected regret. So, yes.
The A, that's the algorithm, is different from the A and the square root, right? That's
yes, the question is this algorithm A is different from this A. This A is the number of actions. So we use curly A for the algorithm and this standard A to be the number of actions. So except a slightly mismatch where in the lower bound we do expectation, while upper bound we kind of prove the high probability result. So typically this mismatch will be resolved if we say for upper bound we can also do some expected regret, and turns out for UCB you can also do expected regret. We will like omit these details. But other than this like slightly mismatch, basically other stuff are like matched with each other. So we'll say in a high level, what we're saying is upper bound, or theorem 1, is more or less saying there exists some algorithm which we kind of explicitly constructed, which is a UCB algorithm, so that for any problem, we have the regret less than blah, blah, blah. And in terms of lower bounds, we're more or less doing the opposite of it. What we're saying is for any algorithm, there exists some problem. So the regret is greater than blah, blah, blah. And if those two are matched, then we say this algorithm is the minimax optimal algorithm. So we can observe a few things from the type of statement. The first thing is, in terms of lower bound, we need to talk about there exists some problem. So a lot of techniques of proving lower bound is basically based on constructing a hard instance. So those are like the most important part of the lower bound. So different from upper bounds, which is the most important part is in the algorithm design, or the lower bound, most important part is in the constructing a hard instance. And also the reason is the second point we want to mention, this is like algorithm independent lower bound. I just want to emphasize this, this point again. The lower bound that we're trying to prove is not saying like UCB VI cannot achieve blah, 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 or Q-learning cannot achieve blah, blah. We're saying like no algorithm can achieve this. Okay, so this is like the strongest type of lower bound you can imagine. And we're using the information theoretical limit. And this is like due to some information theoretical limit. Or statistical limit.
Professor?
Yes.
What's the word in is it hand or hard?
What? This one? Oh, sorry, yeah. Construct hard instance.
What does that mean?
Hard instance means like for specific algorithm, you want to say this algorithm, there exists a multi-embedded so that the regret is high. So that means like for a specific algorithm, you will have a problem which is like very difficult for the algorithm. So that algorithm will suffer very high regret. So hard instance means like you will construct some hard multi-embedded problem, which is hard for the algorithm you're talking about.
Okay.
So for the lower bound is saying for any algorithm, you will be able to find some problem which is very hard to algorithm so that the regret on this problem is like very large.
So what's the meaning of hard in this context?
Hard means like regret is high. This is basically what I mean, yeah.
Okay.
Yeah. Yes?
Should we consider construct a set of hard instances and process their existence? But always exist one instance that achieves the lower bound.
Yes, we will talk more about like how we're gonna construct the hard instance. I think this is a very good point. I think typically, and later we will talk about the techniques because right now on the basic formula, it seems like for any algorithm, we need to construct a hard instance like which is hard for that algorithm, then which is like not very feasible because there are like infinite many algorithms and we cannot just construct infinite many problems. So we'll talk about the techniques, how we're gonna construct some hard instance generically for a lot of algorithms. Okay, so before we talk about the formal techniques of how to construct hard instance, which can be a little bit technical, I first want to intuitively argue why, intuitively convince you why square root t makes sense. So let's first do some entry level, that is, do some warm up, which we will say intuitive argument. Why square root t makes sense. why this is like a fundamental limit where like we cannot actually bypass this limit. So the algorithm, so the like hard instance we can consider in this kind of problem is also quite simple. This is like an intuitive argument, so this is not a formal argument. So let's consider two-arm bandit. Where we have arm 1 and arm 2. So both arms, we have the random reward is drawn according to some Bernoulli distribution. Well, the first arm is drawn with a Bernoulli distribution that reward is like a 1/2 plus epsilon. Well, the second arm is the reward is completely drawn from Bernoulli 1/2. So we consider the case epsilon is extremely small. So you can see if you have a Bernoulli, which is 1/2 versus 1/2 plus something extremely small, typically by just looking at some samples, it's very difficult to tell which arm is better, which arm is the 1/2 plus epsilon 1. So the key thing is hard to tell. From samples. So let's do some like a brief computation on like how many samples we actually need to tell the difference between arm 1 and arm 2. So because we are considered a case where epsilon is extremely small, where we can essentially talk about some asymptotic regime where we, again, in the very beginning, we say we have something similar to like a concentration, where concentration only providing upper bounds, but the central limit theorem basically providing the entire behavior. Okay, so by CLT. By CLT, essentially, we can look at the behavior of R1 bar, which is the empirical average of pulling first arm. Okay, that is, I pull first arm for like a lot of n times, and then I compute the empirical average. That is a summation of all the reward n divided by n. And we know R1 bar is roughly will be equal to 1/2 plus epsilon, which is the expectation, and plus a Gaussian noise. Okay, this is like a bicentral limit theorem, where the standard deviation, the mean is 0, and the standard deviation is 1/4n. Well, the R2 bar, if we also observe like n samples from the second arm, its expectation is 1/2 and plus Gaussian distribution with 0, 1/4n. Okay, this is assuming like we always estimating the empirical average and use this as my as my criterion to say which arm is better. So assuming we're using an algorithm which look at the empirical average and we say like which empirical average is higher, and then we just will pick that arm as my optimal arm or something like that. So we know when standard deviation of this random Gaussian, that is 1/2 squared of n, is actually roughly equal to epsilon or up to some constant. That is, this is like our signal level, that is epsilon, and this is our noise. So when noise is roughly up to the signal level, then we essentially know we have constant probability that R1 bar is less or equal to R2 bar. So that is when this standard deviation is like basically on the same order or even larger than this the signal. Then although the average, the mean of arm1 is higher than arm2, we still have like constant probability. If we just look at the empirical average, this one will be smaller than the R1 bar will be smaller than R2 bar. Okay. So intuitively, in this kind of scenario, we have a constant probability we will actually identify the wrong arm to be the optimal arm. Okay. So basically, we can't tell which arm is better with high probability. That is, with constant probability, we'll kind of like make error. So this essentially indicates that, therefore, we just pick epsilon equal to like 1/square root of n, where this n is like n is just a t, or okay, let's just say 1/square t. Probably up to some constant factor of 2, because we kind of like we pull an arm on like both n times on both arms. So we say if we pick epsilon is equal to roughly something like that, 1/square root t, then we say through the entire interaction with multi-arm bandits for t round we're not sure which arm is better. Therefore, we're more or less doing some random guessing. And in this case, because we're really not sure like which arm is better, like whatever arm I put there with some constant probability is like the wrong arm. So in that case, the expected regret would be roughly something like t is the number of iteration, times each round we're gonna suffer probably like order epsilon error. Okay, because we're really not sure which arm is good. So once we put a wrong arm, we actually suffer some epsilon regret. So in that case, the total regret is something like square root of t. So this is like a bit of intuitive argument why this square root t kind of makes sense, like why this is something happening, why you should not expect something like t to the 1/3 or something even faster than that.
Why is it true when standard deviation is in the same order as the signal, and that means that you don't know which one?
Like we said, when standard deviation is roughly the same order as signal, then with constant probability, R1 bar is less than R2 bar. That
What is that?
that means like a probability, like if you just do some random draw from arm 1 and arm 2, like you put arm 1 for n times, put arm 2 for n times, then with 1/3 probability, arm 1, although has higher mean, will actually have a lower like empirical average. So if you just look at the empirical average, you cannot really tell which arm is better because it can be wrong. The order can be wrong. Yes?
I'm sorry, where does that T omega epsilon come from again?
Oh, the regret, you still remember the regret is computed as a summation of t from 1 to capital T, the Ri star subtracted I_t, right? This is like the definition. Like basically you look at the optimal arm optimal reward you can achieve for t rounds and subtracted by expected reward you receive by pulling your arm. So what I'm saying is essentially because you're not very sure which arm which arm is correct. So on average, in every iteration, you're playing some epsilon error. Like this is like a bit informal argument.
Okay.
Because
Are those, like in that expression I forget, are those like expected values of the reward for each arm? Like so those would be exactly 1/2 plus epsilon and 1/2, or are those also random variables? Like that would be the difference between two variables.
I think this is a bit informal argument, so we'll talk about a formal one later. But here is we're just saying, I think the reason is informal because you cannot make it very rigorous. But basically what I'm saying is once you're not very sure about which arm is the optimal arm, then you're like with 1/2 probability or certain probability, like you may make it wrong. So that's why you suffer omega epsilon type regret like pre-iteration. Yes?
Is it possible to, for regret to have a negative value? Is that possible?
Regret, for this definition, we cannot. Because whatever we have the front is like I star.
Okay.
I star is like the optimal. So I think the regret definition we have here is for stochastic multi-arm bandit, where you can actually define an optimal arm, and whatever you achieve will not be better than optimal arm. But there are some other scenario where if you kind of like you have some adversarial reward. So this is like completely different setting. If you have some adversarial opponent and you're beating with like a best fixed arm in hindsight, in that kind of scenario, regret can be negative. But basically in this class is positive.
Okay, then in this context, the optimal arm means like the expected value of is the maximum, is the
Yeah, in this case, it's just pulling arm 1. Arm 1 has a higher expected reward.
okay. For every case, for every t.
Yeah, for every t.
Okay.
Okay. So that's very good. You ask a lot of good questions. I guess the reason you have a lot of questions is also because, as I said, this is like an informal argument. So we will actually talk about two critical parts that is missing in this argument. Like I think this gives a very intuitive understanding because of CLT and like why the square root t kind of like makes sense. It serves as a sanity check. But on the other hand, there are some problems. The first one is this is like a purely, okay, so problem of this like intuitive argument. The first one, this is like a purely asymptotic. Okay, the reason is like we're using the CLT. CLT requires n go to infinity. So this does not give any like meaningful result when t is finite, or like the rate so in that case it's not very satisfactory. So the second problem of this argument is this argument somehow assume using the algorithm that is going to check empirical average. Check and compare empirical average. Well, this is also somehow like a very unsatisfactory assumption. Like for example, the real algorithm may not look at the empirical average, just look at some other like wild stuff, or like maybe I just always guess some number. So in that kind of scenario, like it doesn't really like rule out some like a very wild or maybe some potentially very smart algorithm. So what we want is a truly algorithm independence. So I hope this warm-up example give you like enough motivation to now formally consider like how we're gonna prove some lower bounds like that. Like helps you like getting some intuition why square root t is like correct order, but we also need more rigorous mathematical tools to prove some lower bounds like that. So we kind of like already noticed the formal argument of this is like the key of doing lower bound is always going to be creating hard problems. So the first strategy of creating hard problem is like this. We just create a fixed hard problem. We'll actually notice this is like a very bad strategy. Okay, this is always an incorrect way. The reason is if I create some problem like this, I would just have like a cheating algorithm which always output arm1, like always put arm1, like blindly. This algorithm doesn't look at any mean or at all, but it just always put arm1. And because I have a fixed hard instance, so there's always one arm that is the best arm. So for that problem, like if I just always put that best arm, and that will always give you like a zero regret. that cannot be hard for that algorithm. So this is not very good. I think the reason not very good of doing like fixed problem is because in the lower bounds, we're actually saying for any algorithm, there exists some hard instance. There exists some hard problem, which kind of like when the algorithm operates on this hard problem, you actually suffer a lot of regret. So this existence of hard problem actually comes after the algorithm. We already said we may want to create algorithm-specific hard instance. So this is a second approach, which is like basically what we stated in the lower bound statement. And that is like the most extreme case you can do. But we already said this also is like a very challenging. This is like a very challenging in math. Like we know there are like tons of different algorithms. So like usually it's very difficult to say like what a specific algorithm and describe the algorithm and do the hard instance for that. So typically we will do like a third way, which kind of like will be more expressive than just a fixed hard problem, but also we want to do the difficulty of construct some algorithm-specific hard instance, which is like too complicated. So what we will do is we will usually consider a distribution over a hard problem. That is, we will not just consider one hard problem, so we will consider like multiple hard problem. And then the true hard instance we construct is basically taking an average or taking some distribution over those specific hard instances. So we're saying on average, this setup problem is like very difficult for our algorithm. Okay. So we'll actually do this approach. So another thing that is difficult to handle is we actually have the random algorithm. It's very flexible. Okay, so this random algorithm can do some arbitrary stuff, which is like very difficult to describe and usually to bound. So it turns out when we accept the formal argument, because we kind of like lose some power when we no longer do this algorithm-specific hard instance. Now we're doing a distribution over a hard problem. When we like sacrifice some power of here, we can actually no longer need to look at the random algorithm. We basically can do some reduction argument. So we say it's sufficient to look at the deterministic algorithm on distribution of hard instances. Okay, so we'll actually do this reduction argument right now. So the reduction will basically reduce, first like reduce the power. So we kind of like lose some power when we no longer construct an algorithm-specific hard instance. So now we're doing just the distribution over a hard problem. But when doing that, we can actually, for free, no longer need to consider the randomized algorithm. We only need to consider the deterministic algorithm. So the formal argument is basically looking at like follows. This is basically a very standard way to do the lower bound. So we start with the lower bound we're trying to prove. So the lower bound we're trying to prove is we look at minimize over all the possible algorithms. let's say in some randomized algorithm. This algorithm A is a randomized algorithm. And we will take a max over, let's call this P. P is the problem, like the multi-arm bandit problem. And we look at this expected regret. Let's use a regret in terms of, regret actually depends on P. So regret actually depends on what kind of multi-arm bandit problem you're looking at, and also depends on the algorithm and the total number of iterations you have. So this is the quantity we're looking at for the lower bounds. That is, for any algorithm, we can construct the hardest multi-arm bandit problem. So we look at the expected regret. Okay. So the first step, we already mentioned that formally we will replace this algorithm-specific hard instance, that is, we're taking max of problem after we're choosing the algorithm, to be some distribution of hard instance. Okay. So we say this is greater or equal to, when we again taking the minimum over algorithm in randomized algorithm. But now, instead of doing maximization over the problem, we're taking problem according to some fixed distribution we will choose later to be the hard distribution. And then we just copy the remaining thing. P, A, T. So this is essentially doing the first step we were talking about. We kind of we lose some power by no longer consider the algorithm-specific hard instance. We're now consider a distribution over a hard problem. Okay, now we will do the second step that will reduce the randomized algorithm to deterministic algorithm. So first benefit we observed by doing this expectation now instead of doing the max is we can actually change the expectation order, because it doesn't matter if we're doing expectation. We can first take expectation over, in terms of internal randomness in algorithm A, and then take expectation over the problem P. So this is precisely equal to we're doing minimization of algorithm A, random algorithm. And we first take over internal randomness inside the algorithm A, and then we take expectation over this problem P sampled from distribution D. The regret. Okay, this is a distribution of hard problems. Okay. So the final step involves a bit of argument of the randomized algorithm. So what is a randomized algorithm? Randomized algorithm essentially is you can view it as a collection of deterministic algorithms. So basically you can view a randomized algorithm that is A and take some input of some internal randomness, internal random coin, okay. So you can think this random algorithm can be always simulated in the following way, that is I have an algorithm, and this algorithm depends on some internal randomness, random bits. So if you're given some like this random bits, you already sample this random bits. This random bits can be like infinite length. If you already sample this random bits, then the algorithm just become deterministic. And the algorithm is random because the random bits is random. So in that case, if I'm minimizing over some random algorithm, then I'm taking expectation over random algorithm. Essentially, I'm like I'm doing minimization of some algorithm of random bits, and then I'm taking expectation over R according to some distribution, some d tilde or something like that. And whatever the remaining thing here. We know the minimizers always achieve at one particular R, because if you are doing R according to some distribution and you are doing the minimizer over the random action, so a random algorithm, so the minimizer is actually achieved at one particular R. So that is basically saying the minimizer is achieved at a deterministic algorithm. So we can, without lots of generality, say this is actually equal to minimizer over algorithm, deterministic algorithm. Okay. So any questions about this? Yes.
Wait, I guess I was confused. So, like, if you take a random algorithm and then you set the R, that becomes deterministic.
Right.
I guess I was wondering, should that not be like a greater than or equal to instead of an equal? Or I feel like the minimum of the expectation should be
It's
the overall.
yeah, overall it's greater or equal, but now the question is like now, because this is like a expectation, you're saying like we say it's we're doing the minimizer of R, so it's like greater or equal. But because on the outside you're actually minimizing over random action, a random algorithm. So if it's greater or equal, then that means your random algorithm is not the best algorithm. So the best randomized algorithm basically will just focus on this particular R. So that's why it's exactly equal. Okay. I think what you said is correct in the sense like okay, let's just be a bit more detailed. So we're saying this is like greater or equal to minimum of algorithm A, random algorithm A, and then we also do the minimum of R of this everything, and this is equal to minimum of deterministic algorithm. So this is, in general, a correct argument, but basically what I'm saying is because you're also doing a minimization over the random algorithm. So basically the best algorithm you will do is basically focusing on R, one particular R. That will actually give you a better algorithm. In terms of if you have an algorithm that will spend some time on some worse R, then that's not an optimal algorithm. So in terms of the minimizing over the random algorithm, this is actually equal. This is actually equal instead of greater equal. But if you're not happy, you just say greater equal. That's also fine.
What is the symbol?
Circle is just copy this thing. Yes.
What is P here? Is that P, right?
P is the hard instance, is the MAB problem, is a multi-arm bandit problem.
Okay, those are hard instances, right?
Hard instance over distribution.
Okay.
Yes,
Which I think
question.
I understand. No, you're saying that the deterministic algorithm that just puts probability 1 on the maximum R or whatever is the minimum random algorithm.
Right, exactly. Yeah.
Professor,
Yes.
when we define regret, we consider the expectation values of viewers, right?
Yes.
Then how do we count the shape of the distribution?
How do we count what?
The shape of the distribution. Do we care the shape of the
Shape of the distribution?
the
The
viewers?
the shape of distribution, you're talking about the reward distribution.
Yeah, that's
I think we don't care about the reward distribution, but when we talk about this multi-arm bandit problem, it's not just the reward distribution. It can also be like which arm has a higher mean and what is the value of those mean. Those are different. For example, I can have one problem that the first arm, the mean is like 1, second arm is mean is 0. Then I have another multi-arm bandit problem, the first arm mean is 0, the second arm mean is 1. So they
also, we don't care about details of those distributions.
We can include that in this multi-arm bandit problem, but it turns out in the proof that doesn't matter much.
Okay,
yeah.
So what we are caring about is the macroscopic picture.
Like how we set up the mean and how we set up which arm is the best arm, that kind of stuff. Okay, so basically the reduction says now we can, in conclusion, so all we need to do is we construct a distribution of problem that is hard to deterministic algorithm. Okay, so this is what we achieved by this reduction. Basically, we start with from the very beginning, from the definition of the lower bounds we have. Now we only need to look at the deterministic algorithm, and we're looking at a distribution over hard instance. Okay. So once we know that, we will now be able to construct the hard instance. So our construction is basically very similar to this two-arm bandit problem. It's just a slightly trick of this problem. So our construction is that we have a different arm, till arm A. So again, the reward of each arm is a Bernoulli distribution. So every arm is 1/2. Only one particular arm A. This like a particular special arm A is 1/2 plus epsilon, where everyone else is like 1/2. Okay, so this is like a special arm. But we already mentioned this, we cannot construct one particular hard instance because there will be a cheating algorithm that always blindly pull arm A. and that will essentially beat this problem. Okay, so this problem will not be hard for this algorithm. So we need to build a distribution over hard instance. So the idea to build a distribution over hard instance is very simple. Essentially, we will sample the special arm. So every problem will only have one special arm, but we will sample this special arm uniformly from a arm. Okay, so what we essentially mean is we're doing a uniform distribution. So the hard distribution is a uniform distribution over MAB with different special arm. Okay, we have such problem. We have like such problems. Okay. That is, I have a multi-embedded problem with the first arm as my special arm, then that is one problem. And then I have a second arm as my special arm, that I have a second problem. In total, I have such a problem, and eventually the distribution is just uniform over all such problems. So in doing this way, essentially, we kind of hide a special arm because this special arm is uniformly sampled from all different possible arms. I actually have no idea which arm it is. Okay, I can no longer have some cheating algorithm just blindly put some arm, and in expectation, that kind of cheating algorithm will actually perform very bad. Okay. So any problem about this construction? Construction is quite simple. So before we talk a little bit more about how we're going to use this construction to prove the formal theorem, let's introduce a bit of notation. We say expectation star. We use this notation as we take an expectation with respect to the random draw of special arm. Essentially, this is like expectation over some meta problem. Okay, we're taking expectation over some like this special arm, which one it is. And then we will use this EA notation and E0 notation. So EA notation is the expectation regarding to the reward. If arm A is the special arm. That is, if arm A is special arm, then what is the reward sequence is probably look like? Okay, I'm taking expectation over that. And finally, we'll do E0 as a reference. Respect to is again also an expectation regarding to all the reward sequence. If there is no special arm. That is, every arm has a one half as a mean reward. And we will use a short notation. We call it R1 to T. R1 to T is actually a collection of all the important information up to T's round. Okay, basically whatever everything environment provides you. That is the stochastic reward you receive at first round by pulling arm A1. Okay. This is like the, let's say, RK, AK, TAT, until this is the stochastic reward. Received at T's round for arm AT, which is the arm learner pull at T's round. Essentially, this is an entire feedback environment give you. That is, the learner will pull A1, A2 till AT, and then they got a stochastic reward that is R1, R2 until RT. So in shortage, we will just denote everything as R1 to RT. When we write this notation of R1 to RT, we really mean this R1, A1, RT, AT. They are taking on different arms. Okay. So given this, we can now basically start by looking at how we're going to formally prove this theorem too. So we look at E star of regret. Okay. This is like first we also need to take expectation over the like meta problem. We even need to take a random draw of special arm. Then in each special arm, we need to take an expectation over the reward we receive. And this is equal to 1 over A summation A in 1 to A, EA. Okay. So essentially, we're saying E star is equal to this this 1 over A, because we essentially define this E star to be an average distribution over multi-embedded with one special arm. And then we can expand the regret in terms of first, the total reward going to achieved by the optimal arm. So no matter which problem instance is, the optimal arm, the mean reward of optimal arm is always 1/2 plus epsilon. So this is a total award, or total values we can achieve by the pulling the optimal arm. And then the value agent is going to receive is the following. Subtracted by summation T. So the agent we're going to receive is always first we have 1/2. And then sometimes we're going to achieve epsilon, sometimes we will not achieve epsilon by the learner. So the only times that we will achieve epsilon is we actually pull the right arm, where we have the indicator function that if the AT, the arm we pull at time t, is actually equal to A, which in this case is the optimal arm. Okay, so we can do some simplification over this formula. That we have 1 over A, summation A from 1 to capital A, EA. What do we have inside? first we have like t over 2 cancel out. Okay, so t over 2 is gone. What we have is we always gonna times epsilon. And the first term times epsilon is t. And the second term times epsilon is the summation over t, where indicator at is equal to a. And that will be equal to na, where na is the number of times we pull arm. Action a is pull. Okay. So finally, we can do some rearrangement because we know the first term epsilon t actually doesn't really depend on this a average over a, doesn't really matter. And this thing only affects the second term. So we can pull it inside, and we actually equal to epsilon times t subtracted by 1 over a summation a from 1 to capital A ea na. So we know the key quantity now. In order to lower bound the regret, we need to look at this EANA. That is, if this arm A is a special arm, how many times I'm gonna pull this A arm? So we're running out of time. In the next lecture, our key idea is we will actually compare this with E0 NA. Okay. That is, in the case of no special arm, how many times I'm gonna pull arm A. So because this epsilon, like the whole idea is, again, this epsilon is chosen to be very, very small. So if we only observe like T rounds of reward, it's very difficult to distinguish this problem versus like the zero problem. So in that case, we will actually say those two are like pretty close. And when these two are pretty close, then basically we'll assume some lower bounds. Okay, and that's the end of this lecture. See you on Thursday.